today's goal of this lecture is, today I will prove the Banach fixed point theorem. What is the Banach fixed point theorem? This theorem is actually fixed point theorem. All of us know what is the fixed point. If F be a mapping from metric space X to X, then X is said to be, the point X is said to be fixed point. If Fx equal to X, is Banach fixed point theorem, which is very useful theorem for differential equation. Using this theorem, you can prove the in ordinary differential equation existence and uniqueness theorem by this theorem. What is the Banach fixed point theorem? The statement of Banach fixed point theorem is, consider X be a non-empty complete metric space. Here the metric space is complete. That means in this metric space every Cauchy sequence is convergent sequence. Then a mapping which map from X to X means F mapping to itself. This mapping is contraction mapping. What is the contraction mapping? I will see few minutes later. If the mapping is contraction, then there exists always unique fixed point. That means by Banach fixed point theorem, always I will get unique fixed point. And this theorem, at first I will say what is the contraction map. We all of us know the ellipsis function. If which map from X to itself is contraction, if there exists real number k ellipses for 0 less than equal to k less than 1, d of fx comma f of y less than equal to k times d of xy. That means distance between the image point always less than equal to k times distance between the original point. This is the definition of contraction mapping, and here this k lies from close interval 0 to open interval 1. Okay, and contraction mapping actually always uniform continuous. Now I will see why the contraction mapping is uniformly continuous. This is very easy proof. Consider one function which map from X to itself is a contraction mapping in XD. Then we have to prove f is uniformly continuous. For this, since f is contraction mapping, then distance between the image fx comma f of y less than equal to k times distance between xy, where k lies between open interval 0, 1. Okay. Now consider epsilon greater than 0 and d of xy less than delta, and consider delta equal to epsilon over k. Then from this equation we can write d of fx comma f of y less than equal to k times d of xy, means this is delta. Here delta equal to epsilon over k. Therefore this is less than equal to epsilon over k. That means this is less than equal to, just omit this part, this is less than equal to epsilon. Therefore d of xy less than delta imply d of fx comma f of y less than epsilon, and this is true for all xy belongs to the metric space X. Obviously this contraction mapping is uniformly continuous. Okay. I hope my all viewers have understood this type of question easily. Okay? Today's goal of this lecture is, actually today I will see the proof of Banach fixed point theorem. But just as a review, at first I will see some new continuous function defined on a metric space. This type of continuous function actually very important for higher study. Today I will define different type of continuity in different metric space. Then I will see proof of Banach fixed point theorem. Let's go ahead. Now we all of us know C0AB. This is actually set of continuous function who is defined on the set AB. Now we all of us know what is the metric space in C0AB. Let Fg belongs to C0AB, then d of Fg equal to supremum x belongs to AB, absolute value of fx minus gx. This is the metric space who is defined on C0AB. And we all of us know C1AB equal to, this is actually continuously differentiable function who is defined on the closed interval AB. And in this space, the metric space is defined as DC1AB is defined as, since this is the continuously differentiable function on the set closed interval AB, this is actually supremum x belongs to closed AB, fx absolute value of fx minus gx plus supremum x belongs to closed AB, absolute value of f prime x minus g prime x. Okay? Obviously, this is the metric space who is defined on the set C1AB. C1AB means the space which is actually set of continuously differentiable function who is defined on the closed interval AB. Consider the differential operator who is defined from C1AB to C0AB. C1AB means continuously differentiable function who is defined on closed interval AB. Now prove that this differentiable operator is continuous between these two metric space. At first think oneself, then see my lecture. At first pause the video, then see my lecture. Definition of continuous function. F from x to y, where x dx and y dy be different metric space, then we can tell f is continuous for if for all epsilon greater than 0, their x is delta greater than 0 such that d with the metric space x comma y less than delta, that imply dy means with the metric space y, fx comma f of y less than epsilon. So continuity of this differential operator from C1 AB to C0 AB, for this actually we have to prove, consider two function fg belongs to C1 AB. Here the metric space is C1 AB. And for continuity, let epsilon equal to 0, epsilon greater than 0. That means we have to prove D with the metric space C1 f comma g less than delta, that imply D with the metric space C0 f comma g less than epsilon. We have to prove this. Consider delta equal to epsilon. Then D with the metric space C1 f comma g less than delta means obviously supremum x belongs to closed AB fx minus gx plus supremum x belongs to closed AB f prime x minus g prime x, this term less than delta. Since this term less than delta, from this equation we can write obviously supremum x belongs to closed AB f prime x minus g prime x, this term would be less than delta. And since I have chosen delta equal to epsilon, therefore this is equal to epsilon. Therefore supremum x belongs to AB, absolute value of f prime x minus g prime x less than delta, which is equal to epsilon. Since here the differential operator, so we have to prove dc0 f prime comma g prime less than epsilon. And from this expression we can tell dc0 f prime comma g prime less than epsilon. Therefore our proof has done. This differential operator, which is mapped from C1AB to C0AB, this operator obviously continuous function. I hope my all viewers have understood this type of proof. This type of proof actually very important. Okay? Oh well. Our next example, all of us know, suppose F be a mapping x to y, where x and y to different metric space. If this mapping is continuous and X be a compact metric space, then this continuous mapping is always uniform continuous. We all of us know this property. Now consider one example which is defined AB cross CD to R and given f is a continuous function. Now define new mapping G of y, which is equal to integration a to b fxy dx. Here, since f defined on a compact metric space and given the function is continuous, that implies obviously the function f is uniform continuous. By this theorem we can tell this. But here g is new function. We have to prove this integration operator is continuous function. For this, I will use actually the sequential criteria of continuity. For this, consider yn be a sequence. Since here g of y, that means y belongs to in the closed interval CD, therefore the sequence yn belongs to the closed interval CD such that this yn converges to y. Now you want to show g of yn converges to g of y. Then we can tell by sequential criteria g is uniform continuous. Limit n tends to infinity gyn means limit n tends to infinity integration a to b f of x yn dx. Okay? And we all of us know limit and integration always interchange. That means this is equal to integration a to b limit n tends to infinity f of x yn dx. Okay? Since given f is continuous, therefore limit n goes to infinity f of yn would be f of y mapped to f of y By sequential criteria we can tell. Therefore, this limit n goes to infinity, f of x y n tends to f of xy dx, and f of xy dx is equal to actually g of y. That means limit n goes to infinity, g of yn goes to g of y. Therefore, our proof has done. By sequential criteria we can tell our new function g is continuous. I hope my all viewers have understood this type of question. This type of question actually very important for higher study. Okay? Well. Now let's come back our original discussion, Banach fixed point theorem. Now I will see our main goal of this lecture. I will prove contraction mapping. And statement of the contraction mapping is every contraction mapping on a complete metric space has a unique fixed point. For this, consider a sequence xn equal to x1, x2 up to xn, and T be a contraction mapping which map T from x to x, and consider one arbitrary point x0 in the metric space X such that the mapping is such that x1 equal to Tx0, x2 equal to Tx1, x3 equal to Tx2, and xn equal to Txn minus 1. Okay? And since x2 equal to Tx1, therefore, and x1 equal to Tx0, therefore, just put the value, this is T of Tx0, that means this is actually T squared x0. Similarly, since x3 equal to Tx2, here I have got x2 means T squared x0, that means this is T cube x0. Therefore, I have got x1 equal to T of x0, x2 equal to T squared x0, x3 equal to T cube x0. Similarly, xn equal to Tn x0. I hope my all viewers have understood this part easily. Now, since given this mapping is a construction mapping, so d of tx comma ty obviously less than equal to alpha times d of xy, where for all xy belongs to x, then d of t square x comma t square y, this would be less than equal to, since here t square x t square y means t of x, therefore this is less than equal to alpha times distance between t of x comma t of y, and since distance between tx comma ty less than equal to alpha times distance between dxy, this is less than equal to alpha square times distance between x comma y, and similarly this would be continued, that means distance between tnx comma tny less than equal to alpha to the power n distance between x and y, where these x and y belongs to the metric space X. Now we have to prove the sequence xn is a Cauchy sequence. For this, we all of us know we have to prove distance between xm comma xn less than epsilon, where n greater than m. Consider n equal to m plus p. Okay? This is distance between xm comma xm plus p. Distance between xm comma xm plus p means distance between t to the power m x0 comma t to the power m plus p x0. Okay? And this is, and we can write this as distance between t to the power m x0 comma t to the power m times t to the power p x0. Okay? and distance between t to the power m x naught times t to the power m times t to the power p x naught means this is by this inequality distance between tn x comma tn y less than equal to alpha to the power n d of xy. By this inequality we can tell this is less than equal to alpha to the power m distance between x naught comma t to the power p x naught. Okay, now use the triangle inequality. We can use the triangle inequality such type. Use the triangle inequality here. D of x naught comma t to the power x naught p x naught. We can write this is less than equal to alpha to the power m times d of x naught comma t of x naught plus d of t of x naught comma t of x1 plus d of tx1 comma d of tx2 up to d of t to the power p minus 1 x naught comma t to the power p x naught. Okay, now use this inequality. T of x naught means actually t square x naught, t of x2 equal to t cube x naught. Use this inequality. Then this is t of x1 means t of x naught. This is alpha to the power m d of x naught comma t of x naught plus d of t x naught comma t square x naught plus d of t square x naught comma t cube x naught so on d of t to the power p minus 1 x naught comma t to the power p x naught. T of tx comma ty equal to less than equal to alpha times d of xy. Use the inequality. By this inequality this is alpha to the power 1 d of x naught comma t of x naught plus similarly use this inequality. Then this would be alpha square d of x naught comma t of x naught and this would be continue and here would be alpha to the power p minus 1 d of x naught comma t of x naught. Then just rearrange this term. Then this would be alpha to the power m 1 plus alpha square up to alpha to the power p minus 1 d of x naught comma t of x naught. And this is actually geometric series. And this series is 1 minus alpha to the power n 1 minus alpha if m and n tends to infinity since alpha less than 1. So obviously this term goes to 0. Therefore our proof has done. D of xm comma xn tends to 0 means obviously distance between xm and xn less than epsilon. Therefore the sequence xn is a Cauchy sequence. Is given the matrix space is a complete matrix space. Therefore the sequence xn converges to x. And now we have to prove this x is actually fixed point. That means we have to prove t of x equal to x. And t of x equal to x, this is we have to prove. That means we have to prove distance between x comma t of x tends to 0. For this, just use one triangle inequality. Distance between x comma tx always less than equal to distance between x comma xn plus distance between xn comma tx. And here xn equal to t of xn minus 1. We can write xn equal to t of xn minus 1. Here distance between t of xn minus 1 comma t of x. And this part always by construction mapping, this is less than equal to alpha times distance between xn minus 1 comma xn. Here d of x comma xn is similar as before. Then plus this part. And since xn goes to the limit point x, That means distance between xn comma x tends to 0 as n tends to infinity. And since this is tends to 0 as n tends to infinity, then our xn distance between xn minus 1 comma x, just here one term before. Since xn tends to x, therefore xn minus 1 also tends to x. Therefore this distance xn minus 1 and x, this distance is tends to 0 as n tends to infinity. Therefore distance between x comma t of x tends to 0 as n tends to infinity. And since this distance equal to 0, that means that implies t of x equal to x. Therefore this point x is actually fixed point. I hope my all viewers have understood this proof. Now we have to prove this fixed point is actually unique point. Next we have to prove this fixed point is unique fixed point. For this, consider tx equal to x and t of y equal to y. We have to prove in Banach fixed point theorem, this fixed point is always unique. That means we have to prove x equal to y. t of x comma y. X means t of x and y means t of y. Then just put the value. This is equal to t of tx comma t of y and t of tx comma t of y. By contraction mapping theorem, this is less than equal to alpha times d of xy. That implies d of xy times 1 minus alpha less than equal to 0. But since alpha lies between open interval 0, 1, then 1 minus alpha less than equal to 0, this is not possible. That means only possibility is d of xy less than equal to 0. But we all of us know d of xy always greater than equal to 0. That implies d of xy equal to 0. And if d of xy equal to 0, that implies x equal to y. Therefore, our proof has done this fixed point is always unique fixed point. All viewers have understood this theorem clearly. Okay. Today I will stop here. In my next video, I will discuss some more example about this topic. Actually, this topic is very important for higher study. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos.